Now we are going to start with the second law of motion. We have studied in the previous lecture that Newton's second law of motion, that is, in this law, force is directly proportional to the change in momentum. We did study in the previous lecture that more the change in momentum, more is the effect of the force. So we can also prove this with the help of an example. Let us consider the example of a case of a cricketer. Let's say that we have two cricketers, A and B. Okay, the first cricketer catches the ball by just placing his hands stationary, by keeping his hands stationary. For example, if this is a player A and this is player B, and this player, these are his hands, and a ball is coming, and he just keeps his hands stationary, and ball catches the ball like this. So, what is the result that he's going to get? He probably his hands are going to get hurt. And if this is player B, okay, this is player B, what he does is that he when he tries to catch the ball, he moves his hands along with that ball. So when he comes the ball, he catches the ball, and then with holding the ball, he moves his hands backwards. So he will not get hurt. Why? Because in this case, force is less effective, that force produces less. In this case, force produces more. Why? Because change in momentum here is more as compared to the other case. Why change in momentum is here? Now you can verify this example by doing it yourself as well, but probably if you try to verify this case, you're probably going to get hurt. So okay, here how the change in momentum is more. If I keep my hand stationary like this, obviously when ball is coming towards my hand, there is going to be some change in momentum, and I am not doing anything with my hand. So in the second scenario here, there is no change in momentum, or change in momentum is going to be where this here momentum is not changed. So overall the momentum change is going to be quite big. So here the change in momentum's value is going to be greater, because ball is coming here, my hands are kept stationary, I'm not doing anything with my hand, so momentum produced in this case is quite less. So obviously the change in momentum is going to be more. So in the second case, when ball comes, obviously there is some momentum being produced, and then what I do is that I produce a momentum to in my hands as well. When I move my hands backwards, my hands are also providing some momentum. See, so these are also providing some kind of necessary momentum. So after this, when we calculate the change in momentum, its value is going to be little less. Probably as compared to the first case, this change in momentum is going to be less. So here, when change in momentum is less, the force experience will also be less. So here the cricketer manages to protect his hands from getting hurt. So this scenario we see very often in games. So this is one example through which we can prove that yes, when momentum changes less, so force produced is also less. Now let's try to validate it through an experimentation. Okay, let us consider, for example, let's suppose that there is a body which has mass m, its initial velocity is u, this is experiencing some force for some time t, and after experiencing some force for time t, it attains its final velocity, which is at v. So if I really want to calculate my initial means starting momentum, that's gonna be like mu, right? Because it's product of mass and velocity. Now if I have to produce my final momentum, that is probably gonna be mv, right? So now if I want change in momentum, for time t, for t time I'm calculating, that is going to be like, what is it? It's going to be, obviously what it's going to be, final minus initial, right? Because final is always more. So mv minus mu, that is what it's going to be, final minus initial. Okay, but now if I want the same things, change in momentum, but now I want it for unit time, that is for 1 second. So it's going to be mv minus mu upon t, right? Okay, mv minus mu upon t. So this is my change in momentum per unit time. Okay, I've got my change in momentum also. In the previous class we learned about acceleration, which is change in velocity per unit time, right? Change in velocity. What is the change in velocity per unit time? What is it? Acceleration. So that means v minus u by t is going to be acceleration. So I can write as it my change in momentum. What is it? ma. Why? Because v minus u upon t is a. If I take m common, then what I'm going to get? V minus u upon t. So that this I've directly put ma. So from second law, what is this? Force applied is directly proportional to change in momentum. So that means force directly proportional to ma. If I remove this proportionality sign, I'm going to get a constant like kma. So this is my proportionality constant. Now let us try. Let's put k equals to 1. So now we will get f equals to ma. This is our necessary law. Basically this is your expression for Newton's second law, f equals to ma, and this is very helpful and it will help you in higher classes as well. So after this, let's say, when will the force be called as 1 Newton? This you make it as 1 Newton. When it will be 1? Obviously when mass is 1 and acceleration is 1 meter per second square as well, right? So let us say, how will you define 1 Newton? I can clearly define it from this formula. Like, whenever you do not know how to define something, you just need to remember it, the formula. You will definitely then remember the definition. So 1 Newton force is that force which produces an acceleration of 1 meter per second square on a body of mass 1 kg. So there you have it, your definition of 1 Newton. So with this, we have done our Newton's second law of motion, defined 1 Newton. The next step is going to be Newton's third law.